Hi, I am Andrea Pinto. I am a big data engineer at Agile Lab. Agile Lab is the company that sponsors this event. We are a company with an important focus about the data in general, but particularly about big data technologies. So we work a lot with Spark, with Cloudera, with Kafka. We work on the cloud, AWS, Azure, Google Cloud in premise. We are expert about data mesh. That is a new paradigm. We are an Italian company. We have some office in the whole Italian country, but at Torino, at Bologna, at Milano, Padova, Roma, Napoli, Bari, and Catania. But not only, because there are several people that are on a full remote situation. So now we are organized to be a full remote company. Not only Italian, because there are several people from the rest of the world. We are hiring, so if you like the idea of this company, you can contact us. After on the chat, I put some links, our web page, and also our handbook that is very important for us because it contains a lot of our rules or our values. So I think it's very interesting. And last thing, because after I share also a link for a survey to have some feedback about this meetup, about the topic, and it's very important for us because it's a way for us to improve ourselves and also this type of event. I think it's all. I am very happy to be here with Marta. Marta is a senior developer at Materialize, and Materialize is also the topic of this meetup. I tried it, and it's very interesting as product. So I am very happy to be here with you and with Marta. Thank you very much.
Cool. Thank you for the introduction, Andrea. I'm also really glad to be part of this meetup. So let me just share my screen. I'm going to do a mix of like a slide presentation and also a demo, which might go great or might go terrible. So kind of prepare for that. Okay, I think we're all set. Cool. So like Andrea said, I'm Marta. I am based in Berlin, Germany, and I work as a Senior Developer Experience Engineer at Materialize. And today I'll basically be giving you just basic or a Materialize one-on-one an introduction on how we can use it to do streaming SQL or run SQL on stream. So I would like to start by saying that I'm not going to really rock your world with a completely new query language. Everything that I'll touch upon in this presentation and everything that I will demo uses the same SQL that you use every day, probably the same SQL that you've used since you started your career in data. And that means that if a statement like this makes any sense to you, you kind of also already know how to write SQL that runs on streaming data. But if this was like the gist of it, it would be a pretty short talk. So what I'm hoping to get across today is to show you how easily or how you can use Materialize to build streaming pipelines without having to use more than just what you see in this slide, SQL statements. So starting from the beginning, I want to make sure that everyone is on the same page and that I cover just like some familiar ground to make sure that everyone understands how we get to a point where the idea of using SQL to handle streaming data as well makes at least some sense. And the first step is to think about an OLTP engine, or the traditional relational databases from when databases were invented. So the systems were designed for, or are designed for, high concurrency, lots of reads, lots of writes, and transactions happening at the same time. And in general, they work very hard to make sure that your business data is both consistent and available. But because this type of database is also kind of good, or at least good enough for other use cases, it's also common that they are used as a one-stop shop that can also answer questions about the data that you put in them. So if you use a database like, say, MySQL or Postgres to store, for example, your product stock and orders, you might be running some analytics on it. Maybe you're building some dashboards on top of it. You're just monitoring what's going on in the system and so on. And this might be fine. Maybe your data volume and speed aren't high enough, or maybe you don't have that many users accessing the system concurrently either. But at some point, as your business scales, it's likely that this stops scaling well. So after all these questions that you are throwing at your database are potentially very expensive, and it will start eating away at the main purpose of your database. So it might make it heat up to a point where your read and write throughput might go down, your database may become completely unavailable, and suddenly the idea of just using a single database to cover both of these sides, or like the two types of workloads that you needed to perform, maybe starts sounding like not such a good idea. But these workloads to the right that are eating into the performance of your database are really exciting and valuable for the business. So you still want to keep using them. And what can you do when this happens? So a common next step might be something like offloading these workloads to a second database that is built in a way that is a little more prepared to deal with this kind of analytical workloads. And this is usually an OLAP store where you don't have the same strict requirements for concurrency or availability, but you have other things that you have to optimize for that are kind of tricky to support. So things like complex large transactions, multi-way joins, subqueries, aggregating over really large collections of historical data, and things like this. And this represents a completely different set of things that the system has to optimize for. So now you have two types of databases. The transactional processor on one side holding the source of truth for your data, and the analytical processor on the other dealing with all the complex questions that you want answered about this data. And because, like I said, they have different things to optimize for, these two types of systems also end up having completely different designs. So OLTP systems are generally row-based, which makes them really, really fast for writes, but kind of slower for reads that involve more than fetching like a row or a set of rows. And OLAP systems are usually columnar, so the data is organized in a bit more attribute-friendly way that makes them really, really fast and efficient to address all these heavy analytical ad hoc requests that you want to throw on top of your data. So overall, if you offload your main database to an OLAP store, things cool down a little bit, and in comparison to what we saw initially. But of course that, Murphy's law. So at some point, this will also hit some limitations. And imagine that as the users of the OLAP database start asking more complex questions, or they ask questions more frequently, your OLAP store is also prone to start heating up. So the problem isn't really solved. We are just sort of passing the hot potato from one system to the other. But at least now the impact is more on the side of your business stakeholders than on the actual availability of your whole business. And this finally brings us to streaming and to Materialize. So if we think about the problem in a bit of a different way, let's call it here OLVM, which stands for Online View Maintenance. We can have our analytical system work in a push model instead. So instead of sitting around waiting to be queried, we can proactively listen for changes in the input data, maintain the results for questions that you know ahead of time that you want to see the answer for repeatedly, and make sure that downstream we keep everything fresh without doing more work than is necessary to process whatever is streaming in into your system. So for example, if you have a dashboard, you can push changes to it as the data flows in, instead of having it repeatedly pull the database periodically and ask, hey, did anything change? Send me the latest results. And in practical terms, what this means is that you can tell your OLVM database, hey, I'm interested in asking this question over and over again and seeing how the results vary over time. Can you please pre-compute it for me as the input changes, so I always get correct and fresh results? And this way, so if we're operating under a push model, we don't have to pretend to be surprised that we're seeing the same query being issued for the thousandth time. The processor can just go ahead, incrementally do some amount of work, and instead be proactive in maintaining these results for you over time as it gets new data from the source. Instead of like in a typical database, calculating them from scratch every time based on a snapshot that might not even be fresh anymore. So you might be computing the results for a query on a snapshot that doesn't have the most current changes. So this is basically the gist of Materialize. So it's a database that is purely optimized for view maintenance over streaming data. And we call it a database and not so much a streaming framework or a stream processor, because it walks and talks like a database, as you'll see soon when I start interacting with it. And it still supports all these heavy, complex workloads that we wanted to run before, with another big difference, which is that it can ingest data from multiple types of sources, so including ones that produce data that might not even fit in or are simply too fast for a traditional database in the first place. So you can take, if you look at it, imagine like you have Apache Kafka or you have Kinesis. Maybe you want to do some change data capture, or you want to consume some historical data from S3. And in a typical database, if you try to ingest real-time Kafka data, it will probably die on you pretty soon. So with Materialize, you can take all of this data, you define some transformations as SQL queries, and Materialize, its job is just to maintain the results of these queries as new data is flowing in all the time. So the other idea is also that you can put these results to work immediately, either by directly connecting BI tools to Materialize. You can sync data back to Kafka for event-driven use cases, or you can just interact with Materialize and stream data to applications interactively using some language driver. So like if you have a Node.js app or a Python app or a Rust app, you can totally use that against Materialize to get real-time updates. And all in all, this sounds great on paper, I hope. And it does address the whole issue that we were facing before. of our databases getting overwhelmed by both the amount of data that they are receiving or the amount and the complexity of the requests that people are throwing onto them. So I already talked a lot, and now I want to show you how Materialize actually looks like. And I'll use a demo that has real world data, and for that reason it might work or not, but hopefully it sums up everything that I've been saying so far and you get a better idea of how Materialize works. So what we'll be looking at is basically data that is streaming in from Twitch, the biggest live streaming platform on the internet these days for gaming. And sorry in advance, like I only realized after doing this demo that it's a little bit meta because we're analyzing streams of streams, but hopefully it's not too confusing. I'll just call the Twitch streams broadcasts from now on to make sure that people aren't too confused. So the whole setup is running on Docker. It's available for you to try on GitHub. I can actually drop a link in the chat right now if you want to have a look. Just a second. Okay, just share the link if anyone wants to have a look while I go through it as well. Okay, and so what we have here is like a bunch of services. So let's start with the sources of data. We will have a data generator pulling data in from the Twitch API. It will be doing this periodically, also to not overwhelm my machine. But in theory, like if you had like something like a WebSocket just pushing data out, Materialize would totally be fine with that too. And we're using Red Panda, which you may or may not have heard about. It's Kafka compatible streaming platform, so you can use it as a drop-in replacement for Kafka. Oh, I'm not going to go too much into it. Like if you're interested in learning more about Red Panda, you can do that after this talk. But for now, you can just imagine that this is a regular Kafka broker. It's for the purpose of this demo, it's totally interchangeable. And we'll also have a Postgres database that I will use just to store some reference data that we can join to enrich the events that are coming from Twitch. And then we'll have Materialize, which is kind of the centerpiece here. And what we will do with Materialize is ingest and transform all the source data that is coming from Red Panda and Postgres and transform it just using SQL. And then we are pumping the results out to Metabase for visualization, just so that you can see what we're actually doing. And I know this sounds like a lot of moving parts, but if you want to get started with Materialize, you can just locally install it, and get a much simpler, setup with no Kafka or nothing like that in a couple of minutes. All it takes is just really doing brew install Materialize, basically, or apt, whatever OS you're using. Materialize is a binary, so you can really easily install it and just spin up an instance and start playing with it. Cool. Let me switch to the GitHub repo. I will try to show you how everything works. I got like backup GIFs just in case nothing works. But okay, to get started, like we can bring everything up. I already did that so that we don't have to stay here looking at each other for 5 minutes while all the images build. So let's see. Let's do Docker Compose PS to see what we have running. And you can see that we have all the services up. So the data generator is stopped because I will just manually run it to make sure that the whole demo doesn't fall apart while I'm trying to show you things. We have Materialize. we have MZCLI, which is P-SQL like SQL client that we'll use to interact with Materialize. You could use something else like dbeaver to talk to Materialize, but here MZCLI is just more convenient if you're in a Docker environment. We have our Postgres database that will have our reference data, Red Panda that is receiving the streaming data from Twitch. And that's basically it. So everything is up. Things seem fine. Let me just take this out of the way. And okay, so what we can do right now to make sure that everything is working like it should is to make sure that we have a Twitch streams topic created in Red Panda. So this should be created by the data generator. So just to make sure that we have a topic in our Red Panda broker called Twitch streams. And let's make sure that there is some data landing in there, or that there's some data in there. Okay, cool. So this is working. And here you can see basically what we are receiving from Twitch. This is a broadcast event. So this is a broadcast that is live right now. And yeah, the message structure, it's nothing. So you have like a stream ID, you have the user that is doing the broadcast, you have what game they are playing, you have the title of the stream, you have the language in it in which it's being conducted, and all this kind of stuff. So all of this is coming from Twitch into Red Panda, and we have all this data. Once the data generator is on again, all this data will be just flowing through Red Panda and being persisted in there. This will be your source of truth. And okay, and oh yeah, one thing I wanted to explain as well, each stream has multiple tag IDs, and the translation for this incomprehensible UUIDs are what we will use Postgres to translate. So Postgres has the equivalent, like the string description of that matches these UUIDs. Okay, let's move forward. So now we are ready to enter Materialize land. And like I said, what we'll be using here is, okay, we'll be using the MZCLI, which is the little SQL client to interact with Materialize. And right now, nothing exists in Materialize. So the first thing that we need to do is create our sources. So we need to tell Materialize where to find the data we want to consume. And creating a source is how you do that. So in this case, we'll have, well, like I was saying, a Kafka source, or consuming from, we'll have a Kafka source consuming the Twitch streams topic. And the problem with the source, not with the source, but the problem with the source data is that you will get over time multiple events for the same stream ID or for the same broadcast, but you want to only keep around the latest event for each broadcast. So we want to, for each broadcast, we only want to keep the latest event that we receive. And this is why you see here that we are using an upsert. This means that Materialize will just update or use the input data to continuously update what's coming in instead of continuously appending to it. So, okay, so we need to, this is how we would create a source in Materialize to consume data from Red Panda. Like I said, Red Panda is compatible, API compatible with Kafka. So the way it's supported in Materialize is through the Kafka source as well. And if we create that, cool. Nothing is really happening still at inside Materialize. So right now we just told Materialize where to find the data, but it's not actually consuming any data until we do something else, which I will explain in a bit. Okay, and we're also going to connect to Postgres. Like I said, we have all the reference data there. So let's do that. And the way you connect to Postgres here is, or our Postgres source connector actually does change data capture. So the idea of using the Postgres source here, we're not just doing lookups on Postgres. What this source does is that it keeps track of changes in the Postgres database. So imagine that someone changes a tag description or a tag is deprecated. This will be instantly replicated into Materialize without you having to trigger anything. And we could also just do this using Kafka and Debezium, for example. But I wanted to show an alternative way in case there are people listening who don't run Kafka at all, but still want to do change data capture from a Postgres database into Materialize. Oops. Okay. Okay. Sorry, I already created that. So if you do show sources, we have both of our sources created now. The Postgres source, the Red Panda source. And because what we get from the Red Panda source is basically gibberish, we need a couple of views to transform the data that we are getting from there. So basically, we are just creating views. These aren't really also, again, bringing in any data into Materialize. This is just kind of a statement that you want to have handy and just say, hey, when I use this view in a Materialize view in a little bit, it's just basically an alias to run the select statement that is embedded in it. So we do that. We create views, but you'll see that if I try to select from one of these views, nothing will happen because, again, we're not ingesting any data yet. This is just something that we can reuse within other queries to not have like these huge SQL statements all over the place. Okay, so let me just, from here, now that we have our sources defined, then Materialize knows where to find the data that we want to consume. We can start thinking about some questions that we want to ask. So the rule of thumb with Materialize is that you want to create a Materialized view for any questions that you want to see answered repeatedly, but fast. So let's start with figuring out, for example, what the most popular games on Twitch are. Based on how many viewers are currently watching these streams. So for this, we will do simple aggregation based on the game ID and the game name. And you notice here that I'm using the create materialized view statement. So when I run that, what happens in the background is that Materialize will create an index, or Materialize will index the results of this embedded statement in memory. And as new data comes in, you will see, as new data comes in, you will see that Materialize will just update the results without you having to do anything. And for this, I should actually get the data generator running again. Data generator. Okay, hoping some data so that we can see things change. And now if we do a select statement on top of this materialized view that, like I said, is maintaining the results in memory as new data is coming in from Red Panda, you can see that right now this is kind of like the current overview of what's happening on Twitch. So these are the most popular 10 games. I have no idea what Elden Ring is, but it has 2,000 streams going on. And if we do this query repeatedly, you should see that as more and more data comes from the Twitch API, the results or the numbers that you get returned are updated. This will be way easier to see when I go to the dashboard, because otherwise you just have to consistently, like, repeatedly query the Materialize view to get the latest results. Okay, we can see things like, is anyone playing Doom right now? You see that there's a bunch of people and a bunch of streams of people that still enjoy playing Doom. And give me a second. Okay, so the gist of the whole thing is we created a Materialize view. Materialize is now maintaining the results of the question that we asked of what are the most popular games on Twitch. It's just maintaining it for us as new data streams in. And whenever you throw a question at it, it will be super quick to reply because all the data is indexed in memory. Okay, cool. So this is kind of the core of what Materialize is. There is some magic involved under the hood with the engine that backs Materialize, which is called Timely Data Flow. But in the end, for you as a user, all you need to care about is just writing SQL queries. So we're going to look next into a couple of patterns that only become interesting when you apply SQL on streaming data, and that you might assume that you would need more than SQL or some custom SQL extensions to achieve. So one of the more immediate things that is different in streaming is that time keeps progressing and keeps ticking along with the real world time. So unlike what you may be used to with batch, for example, where your data is kind of frozen in time, or it's kind of frozen at the time that you emit a query. And this means that if we want to ask something like, what streams have started or what broadcasts have started in the last 15 minutes on Twitch, in the last 15 minutes part is a moving target. So as time moves forward, there's a window that has to slide over to catch like the last 15 minutes. So how can you express this using just SQL and without having like any windowing additional syntax? So in Materialize, you can use something that is called a temporal filter. It's what you see here in the slides. It's basically what it will do is it will implement a sliding window, like I was saying before, that will expire the events that kind of fall off this window as time moves forward, and it will pick up new ones. So with the bonus of, like I said, not having to learn any new syntax, and the key here to how all of this works is MZ logical timestamp, which keeps track of the logical time for your query under the hood, and it's kind of comparable to now, or of how now would work in a different database, in a regular database, but applied to streaming. So let me do that now. So, okay. So if we want to know what gaming streams or what gaming broadcasts started in the last 15 minutes, and we want to, keep track of the answers to this question over time, again, what we need to do is create a materialized view. And like I said, this is the temporal filter part, and we will be looking at the past 15 minutes. And now that the materialized view is created, again, we can see how we can get what stream started in the last 15 minutes. Maybe if okay. Basically, sometimes give like ugly results. But this basically what is happening is Materialize. You will see that, like I said, for the MZ logical timestamp, you will see that the minimum started date of the broadcast will progress over time, which is not happening now, I think, because I don't have any more data flowing through it. But you should see that as you query for the minimum started date of the broadcasts, what happens is that, as you'll see here, you can see that time keeps moving forward with your input data and with the actual time in the real world. Okay, cool. And something else that is interesting and that people are usually afraid of doing in the streaming world is doing joins between multiple streaming sources. Like in our case, like I mentioned before, we need to enrich the events that are flowing through Redpanda with the reference data that we are getting from Postgres. And so here, what we want to know this time is what are the most used tags. And if you remember from Redpanda, we are just getting these UUIDs that don't really mean anything if we actually want to know what the tag description is. And this is what we will enrich it with from Postgres. So we will just use a join to kind of create a materialized view that is keeping track of that. And again, you can see here that because there are multiple tag IDs for each broadcast, we first need to unnest that, and then we can do a join between the data that is coming from Redpanda and then the data that we're getting from Postgres. And joins are really one of the things that Materialize does best, and especially something that Materialize does in a sort of a different way to existing streaming systems that makes it really powerful. You can handle like 8-way, 16-way joins with data warehouse grade queries in a pretty efficient way and with less restrictions than other systems. So now let's try to create a materialized view to keep track of this enrichment. Oops. Oh wait, did I forget to create something maybe? I think I forgot to run this. Okay, I just forgot to run the views on top of the Postgres source, and now we should be good to go. We created our enriched view, and we can select from it to get the top 10 most used tags on Twitch. And yeah, so playing with viewers is the most popular one. And like I said, what the we now Materialize is maintaining this join. So if something changes on the Postgres side, we will be able to immediately see it here. So imagine that I log into Postgres and I'm going to update the most popular tag, which is playing with viewers. And I will just change it to say, hey, I want to change the tag description to say playing with aliens. And if you run that and you requery Materialize, you can see that the result, or that this change was propagated all the way to Materialize, handling the join and all of this. Like Materialize really is just listening for whatever changes upstream and propagating it over to the transformations. So we are basically doing a join between Redpanda and change data capture data that we receive from Postgres. And okay, and now this is a bit of a stretch, like one last pattern that I want to show you, even though, like I said, it's a bit more complicated and uses something that even for Postgres users can be a bit exotic, is the ability to do event-driven queries. So it uses a lateral join like you see here in the slide, which is kind of like a for loop for SQL. So let's say that you want to know who the most popular streamer is on Twitch for each of the top 10 games. If you remember, like we wrote a query in the beginning that gets the top 10 games that are currently playing on Twitch. And what you can do with the results of that query that may totally change over time is pass each game in the top 10 as a parameter to the body of this lateral join. And what Materialize will do is only run the subquery for that subset of games. So what this means is that you can have an arbitrarily complex SQL query within the lateral join, and it will only ever be executed for the subset of inputs that you are passing it from this other view. So let's run that. So let's create a view that is just embedding the statement that I used before to show the top 10 streaming games based on the first Materialized view we created. So this is not really doing anything. It's just to save us from having a huge add statement here when we actually run this. And now if we create a Materialized view on this, we should get the most popular streamer for each of the top 10 games, even considering that as new data streams in over time, the top 10 might change. So Materialize will only create this or will only do work for the actual 10 games that are in the top 10. And you see here the name of the streamer that has the highest viewer count for it. And we can actually, for example, we can Montana Black 88 is playing Fortnite. And we can check here, and you can see that the user is live on Twitch playing Fortnite. So, you know, we're getting the freshest data. Materialize is just crunching through it as we get it from the Twitch API. And this basically gives you a way to express a top K over streaming data using nothing but SQL, which is, I mean, admittedly kind of hard to explain, but pretty cool. And okay, so to finish it off, I'm going to now switch to Metabase because, you know, it's really hard to actually see all these things that I'm saying by just looking at my command line with a bunch of SQL statements. So let's restart. Okay, hopefully. Okay, so Materialize is PostgreSQL compatible. So to connect it to Metabase, you basically just you can use the native PostgreSQL connector. You just point it at a different port, which is a default port for Materialize. And this is all you need. You don't need any custom drivers. It works just based on the existing Postgres connector. And hopefully we have some data here. Okay. Now, this is basically data that is in our Materialized views, and nothing is moving because my data generator is stopped. But as soon as I started, so if I exit this, and let me just see if it's up. So if I start the data generator, and I set Metabase to update. Using a little trick to update every second. You should see that data is changing as we are receiving new data from the Twitch API. And this is basically it. So like each one of these widgets is based on one of the Materialized views that we created. And as new data comes in, Materialize will just make sure that all of this is kept up to date. So all you have to do is really define the Materialized views with these queries that you want to keep track of over time. And Materialize is just keeping that up to date and fresh for you with millisecond latency. So we have maybe we can see again, we can go back and rechange rechange the description of the tag, and you can see here that it was instantly updated all the way through to from Postgres all the way to Metabase. Okay, and this is it for the demo. Actually, I think it's way easier if you just go to the GitHub repo and you take some time to go through the demo by yourself. Everything like I showed here, like you just need to Docker compose up the setup, and then everything should be pretty easy to go through for you. So what's the whole big deal with Materialize? On one side, you have Materialize views that are expensive and hard to maintain in a traditional database or a warehouse. And on the other side, you also have advanced streaming systems that admittedly have a much bigger learning curve than a database. So what makes Materialize different? I will make this pretty quick because I'm already speaking for a bunch of time. So the first point is that it uses standard SQL. So you can reuse whatever code you already have, maybe in a different database. It's pretty easy to migrate to streaming with Materialize from, for example, your Postgres instance or a MySQL instance. It allows to do complex multi-way joins and all kinds of data warehouse grade statements. It also supports historical backfilling, so you can bootstrap your materialized views with historical data that you store in S3, for example, and then resume consuming streaming data from something like Red Panda or Kafka. It is Postgres wire compatible. You could see like how easy it was to connect to Metabase just using a regular Postgres driver. You can connect to it using SQL clients like dbeaver in the same way. And you can even use dbt with Materialize to do your transformations and keep track of, like, keep your project organized. And really at the heart of it, and what makes Materialize different to other streaming systems, is the engine that is at its core. So it does incremental computation, make sure that you're not wasting time crunching over data that isn't changing. It's pretty efficient. It's based on timely data flow. It has many, many years of research led by Frank, which is one of our co-founders. And it borrows some techniques from traditional databases like shared indexes that makes Materialize's engine really resource efficient, especially for things like joins. And it allows you to, even with all this complexity, you as a user don't need to do anything else than just write SQL. So all of this complexity of the engine is completely abstracted from you. And whether Materialize is for you, it depends. If you need access to data in real time, if you want to enable new use cases that maybe require sub-second or millisecond response times, and if you need to scale your workloads, but you still want to keep like the language that you've always used, so you just want to use SQL, you don't want to learn something like Java or Scala or Python. It's you want to keep also like the plug and play capability of it. So like I showed, it's pretty easy to just plug Materialize into a bunch of different things. And really, the learning curve is not as high as some other systems because, like I was saying, Materialize kind of hides all the complexity of whatever it's doing under the hood from you. So if you're interested in it, I should give it a try. There's a couple of resources here if you're interested in learning more. And yeah, I'm ready for questions now.
I don't know if someone has some question. Maybe I can start. So I know that you did some contribution to Flink. So sorry, but I have to do this question. Maybe you can do a small comparison between Flink and Materialize, because maybe there are some use case where is better Flink, and other ones where is better Materialize, of course.
Yeah, definitely. So I think that, at least from my experience with Flink, they are pretty different systems in the sense that Materialize feels a lot like just using a database, and Flink is a really full-featured stream processor. So it has a bunch of different APIs. So if you want to just use SQL, you can use SQL with Flink, but then there's a lot more around it that you need to learn about. And it exposes, because it is so flexible and so customizable, it exposes a lot of complexity that you have to deal with. And for me, this is the biggest difference between Materialize and Flink. Materialize is way more focused on a certain type of use cases, and so the scope is much smaller. And Flink is a way bigger, crazier framework if you want to do big, crazy things. Probably Flink is more flexible, but in the end, it really depends on what you need to do. And also it depends on the kind of team that you have, the kind of stack that you already have. So like I was saying, Materialize integrates really easily into common infrastructure, which is not completely true with Flink. So yeah, we try to not do direct comparisons because it always depends on a bunch of different things. But my experience with both systems, I think definitely Materialize is an easier entry point to streaming than Flink would be.
Yes, thank you. I don't know if someone has another question. Maybe not. So I think the topic was very, your speech was very clear, and the topic is very interesting. So thank you very much, Marta. It's a wonderful experience, I think. I want only suggest to the other people to follow our social networks, because we will do another meetup in next month, I think, about Kenso. Maybe, I don't know if with us now we have also the next speaker, not maybe. So I think it's very interesting also this. And thank you very much. And if you want, you can give us a feedback about this meetup. Thank you.
Thank you so much for having me.
Thank you, Marta.